There are all sorts of different problems and different difficulties of problems we could do involving kinematics. So let's say we've got we have a clock, and it has an hour hand that is 3.5 centimeters long. And I want to determine, one, the angular speed of the hour hand, and the linear speed of the tip of the hour hand. Well, what do we know about the hour hand? We know it has a period of rotation of 1 hour, which is 3,600 seconds. So angular speed we know is omega 2 pi over the period. So the angular speed of our hour hand is just 2 pi over 3,600. It should be pi over 1,800. And I don't have a calculator handy, but you could punch that in and get it. Then the linear speed of the tip, we know that linear speed is just omega times r, and our r is 3.5 centimeters, so that's 0.035 pi over 1,800. Right, so you can figure out stuff like that. We could also do things like calculating the angular speed of the moon as it rotates around the Earth. The moon has a period of 27.3 days. That's both its rotational period and its revolutionary period, which is why we only ever see one side of the moon, because it's rotating at exactly the same rate it is revolving at, which is what comes from the phrase the dark side of the moon, is referring to that side of the moon that we never see. It's really not a good name because it's not dark necessarily. It's light just as often as the side of the moon we see, but it isn't visible from Earth, which is how it got its name. Anyway, so the angular speed, the period is 27.3 days. Well, there are 24 hours in a day and 3,600 seconds in an hour. So that's our period. And so then we can take that, and the angular speed is just 2 pi over the period. So we can take that 27.3, it's 2 pi over 27.3 times 24 times 3,600, and we can punch that in and get a number. We can also do problems involving using our kinematic equations. So let's say we've got a CD player that's accelerating the CD at a constant rate of 5.6 radians per second until it reaches an angular speed of 480 revolutions per minute. Determine its angular displacement during this time. Well, first off, revolutions per minute we need to convert to radians per second. That's revolutions per minute. There are 2 pi radians in 1 revolution, and there are 60 seconds in 1 minute. So that's 480 times pi over 30. We can chop off the zeros. 48 divided by 3 is 16. So we got 16 pi radians per second. Okay, and from there, I should say accelerates from rest. Okay. And from there we can use the time-independent equation. 2 alpha delta theta is omega final squared minus omega naught squared. That's 2, 5.6 delta theta, is what you're trying to figure out. Our omega final is 16 pi squared, and our omega naught is 0. So we could use that to figure out the delta theta, so the angular displacement of the DVD. Let's say the CD then slows down to, 22 radians per second. while covering an angle of, I don't know, say 35 radians. And I want to know, how long does this take? Well, in this case, what do we know? We know our omega naught, or sorry, we know our omega final. We know our omega naught from up here, and then we know our delta theta. So in this case, I would use the average velocity equation. We'd say delta theta is half omega naught plus omega final times time. So that's 35. Is half omega naught is 16 pi. Omega final is 22 times time, and calculate the time that way. Right? So, doing rotational kinematics problems is very similar to doing our linear kinematics problems. You figure out what variables you have, figure out what variable you're trying to figure out, and then you apply the appropriate equation. You're more likely to have to do a unit conversion involving revolutions and radians and whatnot. But those are pretty straightforward. But it does add an extra step to solving rotational kinematic problems. Another interesting application of rotational kinematics has to do with rolling motion. And this is talking about when we have a ball or a tire or something that's rolling. And if we are rolling without slipping, meaning there's, the tire isn't sliding at all, it's just rolling, then the linear motion of the object corresponds to its rotational motion. So like for a car, for example, the distance the car has traveled is equal to the radius of its tire times the angular velocity of the tire. The linear velocity of the car is equal to the radius of the tire times the angular velocity, times the angular displacement of the tire over here. The acceleration of the car is equal to the radius of the tire times the angular acceleration of the tire. So those linear quantities relate, these relationships are always true for a point on the object. The distance that point travels is always equal to r times delta theta. But the distance, the linear distance in a straight line the object travels doesn't usually follow this pattern unless objects are rolling without slipping. So we can do some interesting kinds of problems with this. So let's say we've got a bike accelerating from rest. It covers a distance of 52 meters in 7.4 seconds. The bike's wheels are 71 centimeters in diameter. What is their angular acceleration? So this problem incorporates both linear and rotational kinematics. And there are two different ways you can go about doing it. At some point, you're going to have to turn your linear quantities into rotational quantities. So for this one, if you're accelerating from rest and we got a distance, we got a time, I would use the time-dependent equation if I wanted to find acceleration. Okay, I would say that 52 equals, so we're saying x final equals x naught plus b naught t plus 1/2 at squared. We call x naught 0, or b naught is 0 because we're starting from rest. So 52 is half a times 7.4 squared. So then our a is 2 times 52, which is 104 over 7.4 squared. And then our alpha is related to the linear acceleration by this relationship of r alpha. So r alpha is equal to a over r, which is 104 over 74 squared over 71 centimeters. And that's how we could find our angular acceleration. You could also do this at the front end. and say that, oh, if d equals 52, that means our delta theta is 52 over 0.71. Our delta theta would be d over r. And then use the same equation and say, delta theta equals omega naught t plus 1/2 alpha t squared. This is 0 because we're starting from rest, and then we have 52 over 0.71 equals 1/2 alpha times 7.4 squared, and you wind up getting the same answer either way. So with one of these rolling problems, you can either, you'll probably have to convert from linear to rotational or from rotational to linear. You'll probably have to apply a kinematic equation, but it doesn't matter whether you convert everything first and then do the calculation, or do the kinematic calculation and then convert your quantities to the other type. You can go either way, and it's mathematically equivalent. Generally, I would say, well, this one doesn't matter because there's only one quantity to convert. Generally, I would say, if you're given two linear quantities and asked to calculate something rotational, since you already have the two linear quantities, I would do the kinematic calculation in the linear version and then change it to rotational. So I think it would, in most cases, I think it'd be simpler to convert from linear to rotational or rotational to linear at the end, but it might not always be, and it doesn't matter what you do. I was about to do another example, and I realized that I made a mistake here. The bike's wheels are 71 centimeters in diameter, which means that the radius is 35.5 centimeters. So over here, this should be 0.355, not 0.71. Okay. So let's take another example. Let's say a car accelerates from 11 meters per second at a rate of 2.4 meters per second squared for 1.3 seconds. If the diameter of each tire is 45 centimeters, determine the tire's angular velocity at the end of this time. What are we given? Well, we have v naught, we have an acceleration, we have a time. I would go ahead and use a equals delta v over t. So our v final would then be equal to v naught plus at, which is 11 plus 2.4 times 1.3. And then the angular velocity is related to that. Omega is going to be v over r, which is 11 plus 2.4 times 1.3 over r, which is half that. It's 0.225, 22.5 centimeters. So you can see how this works. We pick out what equation we need. We convert from linear to rotational as needed, and then we can solve any of these problems.